Hello, gentle people. My name is Kristen Bradley. Allow me to present to you the research paper titled Stack Overflow Considered Harmful? The Impact of Copy and Paste on Android Application Security. A paper that I did not write but find fascinating. Stack Overflow. If you're anything like me, you frequent Stack Overflow a lot. For those of you not aware of what Stack Overflow is, allow me to make you acquainted. Stack Overflow is a discussion platform for programmers of all levels to share ideas and, often, code. Need to write a for loop in Python? Stack Overflow has that. Need to learn how to exit Vim? Stack Overflow has your answer. Need to write infrastructure as code so that you can deploy resources in AWS? Stack Overflow has code for that too. Note that you're not alone if you copy and paste code from Stack Overflow. Both new developers and seasoned professionals copy from Stack Overflow from time to time. However, do you ever stop to think about the security of the code you're copying from Stack Overflow? Are any code snippets on Stack Overflow secure? Since professionals copy code, how many of these insecure code snippets end up in production level applications, such as those on the Google Play Store? This paper seeks to provide an answer to those questions. Now, before we go diving into this paper, let me provide you with a little background info. First, let's discuss the ancestors of this research paper. Several assumptions in this paper can only be made because of the research that came before it. For example, this study depends on numerous other papers that define proven secure and insecure practices. Some of those papers focus on cryptography, while others discuss the concept of least privilege in application permissions. Additionally, this paper is by no means the first to discuss insecure code copied from Stack Overflow. More specifically, it's not even the first paper to discuss insecure Stack Overflow code copied into Android applications. For example, see the paper titled You Get Where You're Looking For, The Impact of Information Sources on Code Security, published in 2016. Furthermore, this paper also relies on previous research done in the field of machine learning. A code analysis of this scale would be infeasible without some level of analysis automation. While we're on the topic of machine learning and automation, let's move on to the next part of the background, what you'll need to know to fully appreciate this paper. First, to appreciate the analysis method, you need a basic understanding of what machine learning is and how it works. Machine learning is basically teaching machines how to learn like humans do, which involves practice and gradual improvement. To describe it another way, think about how you would train a machine to point out pictures of stoplights on the road. You would give the machine a bunch of pictures of stoplights and say, these pictures have stoplights in them. You would then show the machine a bunch of other pictures without stoplights in them and say, these pictures do not have stoplights. You then give the machine a study method. In essence, you tell the machine how to learn. From that point forward, you give the machine a bunch of pictures to train on, and the machine gradually gets better at telling you which pictures have stoplights in them. So the next time a CAPTCHA asks you to click all the pictures with stoplights in them, think about that machine you're helping to train behind the scenes. Next, you will need to understand certain security protocols, such as TLS or Transport Layer Security, symmetric cryptography, asymmetric cryptography, one-way hash functions, and random number generation. This paper does describe what is considered secure and insecure for each item, but the reasoning might not make sense if you do not have the background knowledge. Another two topics you will need to understand regarding math are set theory and linear algebra. While I expect that most of you listening to this presentation have taken courses involving these topics, there are a couple of sections in this paper that read quite densely unless you brush up on that knowledge. And so, for the sake of brevity, I will not be going over the detailed math behind this paper. Also, keep in mind that this paper was published in 2017, and the data analyzed was from 2016. Numerous other Stack Overflow posts and Android applications have been created since then. That said, the methods in this paper are still relevant, but the raw numbers might be out of date. So, to recap the background, remember that this study works off the foundation of other research papers that came before it. Note that this isn't even the first paper to combine security, Stack Overflow, and Android applications. To fully enjoy the paper, make sure that you have some general understanding of machine learning, common security protocols, such as TLS and symmetric cryptography, set theory, and linear algebra. And finally, remember that while the methods in this study are still useful, the numbers listed in the analysis are likely out of date. Now that the background is out of the way, let's move on to the research paper. First, we should take a moment to define the key research question for this study. What is the impact of copied and pasted code from Stack Overflow on Android application security? This question means that the paper does not dive into the effects of copy and paste code for other types of applications, such as those in the iOS App Store. It only focuses on Android applications within the Google Play Store. This research question also means that the paper does not dive into code copied from other websites such as Reddit or Confluence. All the code analysis performed is done on code snippets found in Stack Overflow. Keeping the research question in mind, let's move on to the research method. So, fun fact, the entire processing pipeline is fully automated. This means that everything from code extraction through clone detection is done automatically. Note that the figure on this slide represents the processing pipeline. The processing pipeline flows from left to right. Starting from the far left, the first step is to scan all posts tagged as Android on Stack Overflow and extract all the code snippets within those posts. The second step in the pipeline is to filter which of those Android-related code snippets are also security-related, thereby shrinking the dataset. The third step is to use machine learning to label the filtered code snippets as either secure or insecure. The fourth step in the pipeline is to generate an abstract representation of each security-related code snippet. The fifth and ultimate step is to use the abstract representation of each code snippet to detect their clones in the Google Play Store. So, to reiterate, the processing pipeline extracts the Android-related code from Stack Overflow, filters out non-security related code, labels each code snippet as secure or insecure, creates an abstract version of each snippet, then hunts for that abstraction in apps on the Google Play Store. Now, let's discuss some specifics regarding the pipeline steps. For step 1, code extraction is done by searching for Stack Overflow posts tagged as Android and extracting anything within code tags. On the top of this slide is a code snippet from a question tagged as Android on Stack Overflow. On the bottom of this slide, you can see that the snippet exists between code tags and its HTML representation. From step 1, code extraction, we move on to step 2, filtering. The goal of this step is to filter out code snippets that are not security related. This step does assume that all security-related code is also Java code. Although it is possible to develop Android apps in C and C++, Google does not promote them since Java is the official language of Android development. Therefore, the rest of the processing assumes that snippets consist of Java code. So, in order to filter in code snippets that are security-related, the research team assembled a set of APIs and libraries that are commonly used for security purposes. The table shown on this slide is the condensed list of cryptographic libraries used for filtering. Any code snippets that reference one or more items in this list are considered security related. Now, that's great and all, but code snippets on Stack Overflow are often incomplete or incorrect. So, how do you determine which API a code snippet references? Well, in order to determine which API a code snippet references, you need to have the fully qualified names of the code elements in the snippet. In this case, you can think of fully qualified names as package names in Java. The problem is that Stack Overflow code snippets generally only contain partially qualified names. A partially qualified name consists of class and method names, which do not have to be unique. So, to change partially qualified names to fully qualified names, this step uses a tool called Java Baker. Java Baker allows the user to define a set of APIs to search for within a snippet of code. If Java Baker returns a result, then that code snippet uses one of the listed APIs. If Java Baker returns nothing, then that code snippet does not use one of the listed APIs. Putting this all together, step 2 picks a code snippet, then processes it through Java Baker, where then Java Baker scans the code for user-defined security APIs, and if Java Baker returns anything, that code snippet is security related. Alright, at this point the method has gone through step 1 extraction and step 2 filtering. Now we move on to step 3 classification. Now that the pipeline only contains security-related snippets, the focus shifts to whether or not the code is secure or insecure. This step is where machine learning comes into play. However, before we can send the machine off to learn, we must give it study material first. To create this material, the researchers manually categorize and label a subset of the code snippets as secure or insecure. 2 researchers review each snippet in the subset. When there are conflicting labels, a third researcher resolves the conflict by listening to the reasoning behind each label. To keep labeling guidelines consistent, the code snippets are also placed into at least one of the following categories: TLS, symmetric cryptography, asymmetric cryptography, one-way hash functions, and secure random number generation. Each category contains a set of agreed-upon rules that define what is secure and what is insecure. An example would be a code snippet that utilizes RSA with a 1024-bit key. Because the code snippet uses RSA, this is categorized under asymmetric cryptography. From there, we can reference the guidelines for asymmetric cryptography. Since any RSA key less than 2048 bits in size is considered insecure, this code snippet is labeled insecure. Once the research team finishes classifying the subset of code snippets, they have training material for their machine to learn. Because the code snippets are sorted into either secure or insecure categories, the security scoring of code snippets can be seen as a classification problem. In this case, it is a binary classification problem. Since this is a binary classification problem, the research group employs the Support Vector Machine, or SVM, learning model. Note that the Support Vector Machine learning model is the study method for the machine to use. Put very simply, the SVM examines the tokens present in code snippets and determines whether or not those snippets are secure or insecure. Tokens are any combination of alphabets and symbols, such as words like while or return. The SVM attempts to check for tokens that are important, that is, tokens that are likely to affect the security of a given code snippet. The figure on the right side of the slide shows an illustration of the SVM binary classifier. The SVM classifies positive and negative cases, aka secure and insecure cases, though the study does not explicitly define which is which. The portion that looks like a road running up the diagonal of the illustration is a margin of error. The margin identifies a small area where the machine is allowed to misclassify training samples while the machine is learning. So, how exactly does the research group define important tokens? It isn't feasible to manually define the importance of every token given its context. To measure the importance of tokens, the research team employs a feature extraction method named the TF-IDF vectorizer. The TF stands for term frequency, how often a token appears within a code snippet. The IDF stands for inverse document frequency, the inverse number of documents a token appears in. In this scenario, a document is a code snippet. The TF-IDF score for a token is the multiplication of the term frequency and the inverse document frequency. Effectively, the TF-IDF score applies a weight to a token. This weight is used to determine how much a token will affect the classification of a code snippet. So, for example, the TF-IDF score of the word return, which might appear once or twice in many code snippets, will affect the security classification differently than a variable name that is used multiple times but only appears in a single code snippet. A condensed description of step 3 is manually label a subset of code snippets as secure or insecure. Use the TF-IDF vectorizer extraction method to populate weights for tokens within code snippets. Feed the TF-IDF vectorizer output and manually labeled snippets to the SVM. Have the machine use the SVM learning model to train on the given inputs. Let the machine learn and automatically label the rest of the code snippets as secure or insecure. Now we're at the penultimate step. Step number 4, abstraction. I imagine you might be asking, how are we supposed to compare source code with application binaries? Well, I'm glad you asked. In order to compare the remaining code snippets with compiled Android applications in the Google Play Store, the code snippets must be abstracted. Both the code snippets and Android applications must be transformed into the same intermediate representation, or IR for short. To transform both code snippets and Android applications into the same IR, the research team utilizes Walla. Walla provides static analysis capabilities for Java bytecode and related languages. First, in order to compile the code snippets into an IR format, the method requires the use of partial program analysis, or PPA. PPA is specifically designed to create complete and typed abstract syntax trees from source code of partial Java programs. On screen is an example of a successful PPA analysis performed on a small, incomplete application. Partial program analysis is important because Stack Overflow code snippets are often incomplete. This research group modified Walla by integrating PPA. This allows the pipeline to transform incomplete code snippets into Walla's intermediate representation. It is worth noting that there are some code snippets that cannot be compiled because they are either too erroneous or contain uncommented text and are thus rejected by Walla. These uncompilable snippets are ignored in the rest of the process. Note that, since Walla operates on JVM bytecode, the pipeline utilizes Google's Injarify tool to convert Android APKs into JVM bytecode. As a result, the Stack Overflow code snippets and the Android applications are converted into the same Walla IR format. The condensed version of Step 4 is as follows. Convert Stack Overflow code snippets into Walla's IR format using partial program analysis. Convert Android applications into Walla's IR format using Google's Injarify tool. Ignore any uncompilable code snippets. We have now reached the final step in the pipeline. Step 5, detection. Since intermediate representations produced via PPA are likely to be different than IRs produced via Injarify, you're not likely to see full matches between code snippets and Android application code. So, how do you verify that code is copied if it doesn't appear the same within the Android app? To handle this, the researchers use a detection algorithm that is robust to fractional and non-malicious modifications. This means that the detection algorithm can handle changes due to compilation and decompilation, but not due to actions such as code obfuscation. The detection method is a modified approach of that used in the DNA Droid tool, which was created by a different research group to detect Android application clones. An important limitation of this tool is that it works best on large sets of code. When code snippets have very few lines, the algorithm is more likely to incorrectly label two sets of code as clones. To combat this issue, the researchers apply a stricter approach which additionally compares constants and method names that belong to a semantic block. A semantic block is a subroutine or set of subroutines that function together for a specific purpose. Note that this strict approach does require that constants not be modified. To avoid computational overhead, the researchers limit the list of classes to search for within code snippets to be solely classes that contain security-related API calls, such as the ones used back in step 2, filtering. Now that we've gone through the entire pipeline, let's quickly recap the steps. Step 1, extraction. Pull Android-related code snippets from Stack Overflow posts. Step 2, filtering. Filter in security-related code snippets based on whether they call security-related APIs. Step 3, classification. Label each security-related code snippet as secure or insecure via machine learning. Step 4, abstraction. Transform code snippets in Android applications into the same intermediate representation to prepare for comparison. Step 5, detection. Determine if the abstracted code snippet appears in the abstracted Android application. So we've covered the research method, but does the study answer the research question? Remember, the research question is, what is the impact of copied and pasted code from Stack Overflow on Android application security? Well, let's see. There was a total of 4,019 security-related code snippets found in Android posts on Stack Overflow. Out of over 1.3 million scanned Android applications, the pipeline detected that 15.4% of them contained security-related code snippets from Stack Overflow. Out of the 15.4% of Android apps that contain security-related code snippets, 97.9% of them contained at least one insecure code snippet. That means out of over 1.3 million scanned Android applications, about 196,403 applications contained insecure code snippets from Stack Overflow. That's a hefty chunk of applications hanging around the Google Play Store. Let's break down the insecure applications into categories. Interestingly, the application category with the most detected insecure snippets was non-casino games. However, insecure snippets run the gamut of application categories. Unfortunately, several thousands of applications that contain sensitive data also include insecure code snippets. This sensitive data could be personally identifiable information such as names, addresses, and banking information. This sensitive data could also be protected health information such as medical history and current medications. Separately, insecure code snippets seem to be the most present in mildly popular applications. However, even applications with over 1 billion downloads are susceptible to insecure copy and paste. Ultimately, given the wide range of applications and the sensitive data several apps contain, the security impact of copying and pasting code from Stack Overflow cannot and should not be overlooked. While the study does have valuable information, we should certainly acknowledge the study's limitations. For starters, only free apps were downloaded and scanned from the Google Play Store. Therefore, it's unknown how paid-for applications may skew the data. Another limitation comes from the filtering step. While the filter does detect security-related APIs, some of those libraries may have uses in a non-security context. Therefore, more code snippets may be marked as security-related than are actually present. A further limitation exists in the classification step. The study mentions that the review decisions are based on widely accepted best practices. However, the security of most code snippets depends on the input values. Therefore, the results may skew in either direction, either over-reporting or under-reporting insecure APIs in Android applications. Before we conclude, let's discuss the impact this study has had on its successors. Other research papers have cited this study over 100 times. Some of those papers cite this study just to use the resulting data as part of their premise. Other papers use this study as a foundation to further expand on the issue of sharing insecure code. For example, see an empirical study of C++ vulnerabilities in crowdsourced code examples, published in 2022. This paper also suggests ideas for countermeasures against copying insecure code from Stack Overflow. For example, as of this paper's publish date, since the classification pipeline is fully automated, the researchers are actively working on a browser plugin for Firefox and Chrome that will detect insecure snippets anywhere on the web, not just Stack Overflow. That said, browser extensions developed by other teams that do something similar are also in the works. Now to conclude this presentation. The purpose of this research paper is to investigate the impact of copied and pasted code from Stack Overflow on Android application security. To investigate, the research team uses a fully automated pipeline to 1. Extract Android-related code snippets from Stack Overflow posts. 2. Filter in security-related code snippets based on whether they call security-related APIs. 3. Classify each security-related code snippet as secure or insecure via machine learning. 4. Abstract code snippets and Android applications into the same intermediate representation to prepare for comparison. 5. Detect if the abstracted code snippet appears in the abstracted Android application. Out of over 1.3 million scanned Android applications, over 196,000 apps contain insecure Stack Overflow code snippets. Thousands of those insecure apps contain sensitive information, such as medical and banking information. Finally, if you have any questions or just want to know more information about this study, then I highly encourage you to read the paper. I will leave a link to the research paper in the description box. Thank you for watching.